Okay, well, thank you very much. I also would like to thank the organizers for inviting me and for putting together this wonderful conference. I really have been enjoying listening to so many talks that discuss time-dependent phenomena in one place. And today I'm going to tell you about some of our work on non-equilibrium phenomena in two-dimensional electronic systems. And before I do that, I want to make sure I acknowledge my collaborators on this most recent work. They are Lily Stanley, Ping Lin, and my longtime collaborator, Jan Jaroshinsky. And the samples that we have been using for these studies were fabricated at IBM. So there are most phenomena in nature are actually far from equilibrium, but we, of course, are focusing on quantum materials. And as we already heard in many of the talks, these materials typically have a number of degrees of freedom that compete with each other: charge, spin, lattice, orbital, and all this gives rise to many complex phenomena, as we've been hearing for the last several days. Now, we want to focus on the simpler case, where we have only the Coulomb interaction and disorder. So I want to show you that even in this simpler situation, the interplay of these two effects gives rise to non-trivial, non-equilibrium behavior that is not well understood. And in particular, I'm going to discuss two types of such phenomena. These are glassy behavior and many-body localization. So these phenomena, these types of dynamics, have been studied in a variety of systems, but their studies of the dynamics of this kind in electronic systems have been relatively scarce. So I will argue and show you that a strongly disordered 2D electron system in silicon is actually an excellent platform for studying these types of dynamics. And in our experiments, we perform time-resolved conductivity measurements. So what we have found is that in the case of a long-range Coulomb interaction, the strongly disordered 2D electron system exhibits glassy dynamics, whereas in the case of a short-range Coulomb interaction, the dynamics is completely different, and in fact, it is consistent with many-body localization. And at the end, I will discuss some possible directions for future research. So again, most systems in nature, including ourselves, find themselves far from equilibrium, and many phenomena exist only under far from equilibrium conditions, and they include, for example, clustering of matter in the universe, down to various types of turbulence on the Earth, to avalanches, earthquakes, down to molecular processes that form the basis of life. Non-equilibrium behaviors are also very important for industrial applications. For example, many pharmaceutical industry relies on transportation and handling of granular matter, such as powders and pills. Also in agriculture, there are fertilizer, pellets, grains, seeds, and so on. So the inherently non-equilibrium behavior of such systems is not sufficiently well understood, and so it is important to understand it both for fundamental reasons and for practical applications so that we can control these processes. So the far from equilibrium behavior is ubiquitous in nature. So one way for systems to reach the far from equilibrium regime is by driving, if we supply them with some energy. And we already heard a number of talks where pumped probes are used to inject energy into the system, and so they are far from equilibrium. On the other hand, there are also systems where even if you remove this external driving force, they remain trapped in states that are far from equilibrium for a long time, at least on experimental timescales. They're not able to equilibrate. And for that reason, they retain a memory of the preparation conditions. So in this talk, we are going to focus on these systems. So we are not studying driven systems, but instead systems that remain trapped in states far from equilibrium. Best known example of such systems are glasses. Everybody is familiar with structural glasses, such as window glass. So these are basically liquids that when you cool them very rapidly, they are unable to reach the lowest energy state, which is that of a crystal, but instead they get trapped in some random configurations for a long time. And this is so they can move very slowly, and this is reflected in the exponential increase of their viscosity as you lower the temperature. So here are some examples of viscosity on a logarithmic scale for several glass-forming liquids. Another well-known example from hard condensed matter physics. This is the inverse temperature. The inverse temperature, and this is the glass transistor temperature. This is the temperature where this change in the dynamics starts to be observed, not necessarily a true thermodynamic transition. So a well-known example from hard condensed matter physics is our spin glasses, such as conventional spin glasses, where we have a relatively small number of or percentage of magnetic ions, such as manganese or iron, distributed randomly within a metallic host, such as copper or gold. So these spins, they interact with each other. Every spin interacts with another one, and below a certain temperature, they are frozen into these random configurations. And this is because the system is frustrated because of the disorder. It cannot find a unique orientation for all of these spins. And the frustration is usually illustrated by everyone, I think. If you consider spins that can point up or down that are placed on a triangular lattice, and you say that they have antiferromagnetic interaction, so they want to point in the opposite direction. So if you place two spins, then there is no way you can place a third spin, so to minimize the energy with both of the other spins. So the system is frustrated. So what about electronic systems, which is the subject or topic of our interest? Well, in low-density electronic systems where potential energy dominates, and again, we are considering only Coulomb interaction and disorder. In the absence of disorder, if we had only Coulomb repulsion, it would favor a uniform distribution of electrons to minimize the energy. On the other hand, the disorder itself favors a non-uniform density distribution. So clearly, if you have both of these present, there is no way for the system to satisfy both of these requirements. We have a frustration in the system because there is no good solution. And it was shown decades ago numerically that in that case, this gives rise to the emergence of exponentially many metastable states with similar free energy. So you no longer have a unique ground state. Instead, you have many of these minima which correspond to metastable states. So each minimum really corresponds to a different configuration of the electrons. So this is called a Coulomb glass. And as a result of this kind of free energy landscape, the dynamics is very slow because the system gets stuck in one configuration for a long time. Then after some time, electrons collectively rearrange themselves, and they can transfer into another metastable state. So the presence of this kind of rugged free energy landscape is actually a unifying concept, a common feature of all glasses. So again, each minimum corresponds to a long-lived state, a metastable state. These minima are separated by barriers with many different heights. So as a function of time, the system gets stuck in one of these states, and on experimental timescales at least, it can explore only a small fraction of this free energy landscape. In other words, since it cannot explore the entire phase space, the system is not ergodic, and this is why standard tools of statistical mechanics cannot explain the properties of such systems. So this glass problem was a problem for a long time, and theoretical mathematical formalism that to describe glasses was developed first in the context of spin glasses by Giorgio Parisi, and this approach also proved useful in other areas of science, and this is why he was recently awarded the Nobel Prize in Physics. Another point that I would like to make here about glasses that will be relevant for later in the talk is that glasses, their properties, their behaviors are very robust with respect to coupling to an external bath. So at low enough temperatures, thermal fluctuations may just help the system go from one metastable state to another, but as long as we have this rugged energy landscape, you will observe the same kind of a glassy behavior. So in recent years, in the last 15 or so years, there has been a lot of interest in the problem of thermalization in quantum antibody systems that are well isolated from the environment, such that when you prepare them far out of equilibrium, they evolve under their intrinsic quantum dynamics. And the question is, what happens at long times? Does the system reach thermal equilibrium or not? So in systems that are ergodic, different parts of the system can exchange particles and energy, and the system will reach thermal equilibrium. Its properties will be described by equilibrium statistical mechanics. But in this process, the quantum information that was encoded in the initial state is lost with time. So there has been a lot of interest, a lot of work, and here are just some of the review papers in this area. There has been a lot of effort to try to find mechanisms that break ergodicity, but that preserve some memory, that preserve some of this quantum information at long times. And obviously, this is of great interest for quantum information science. And indeed, several such mechanisms have been identified, but many-body localization is the only known robust mechanism that breaks ergodicity and leads to the failure of thermalization. Many-body localization is a mechanism for strongly disordered systems to avoid thermalization. And indeed, this is an extension of the well-known Anderson localization for single particles in the presence of strong disorder to interacting systems. So in Anderson localization, particles are localized in space, wave functions decay exponentially, there is no transport of particles, conductivity is zero, so the system is not able to thermalize. This system is not ergodic. So the question was, if we add some interactions, can we preserve this property of non-ergodicity? And indeed, it was shown that under certain conditions, for sufficiently strong disorder, sufficiently short-range interactions, this now called many-body localization can persist such that the conductivity will remain zero even up to some finite temperature. So, as I already said, the disorder needs to be sufficiently large. So, when you have a system in the MBL phase, if you prepare it far out of equilibrium, and this is typically done by performing quantum quenches, which means you change a parameter of the Hamiltonian instantaneously, and then you look at the time evolution of your observables. So if you prepare it in such a way, then it should not be able, it is not able to reach thermal equilibrium. It remains stuck in one state, basically. So, as I already said, there has been a lot of theoretical effort to understand and explore this problem, many-body localization, but some important questions remain open regarding the stability and the existence of the MBL phase. For example, it is not well understood precisely how the range of interactions affects the dynamical behavior and the existence of MBL, and whether a true MBL phase can even exist in systems that are infinitely large at infinitely long times. And in particular, whether the MBL can exist in dimensions larger than one. Recently, the existence of a true MBL phase has been questioned or challenged even in one-dimensional systems. So this is still maybe an open question or maybe a subject of disagreement, I'm not sure. But in any case, there is a consensus that even if the system does thermalize at infinitely long times, on short enough time scales, it can exhibit the dynamics of the MBL-like dynamics. And the properties of this so-called pre-thermal regime are really the key open question in the field, and also the question about the nature of the transition to the putative MBL phase. So this is also going to be a subject of our work, and as I'll explain in more detail later. So this is the theoretical background. Now, experimentally, there has been, MBL has been reported in several synthetic many-body systems that are listed here. Most of those systems were one-dimensional, but MBL has been reported also in 2D systems, in particular in these cold atoms in optical lattices. And I will show you the first such example. This was the example of a bosonic optical lattice, but later they also did experiments on fermionic lattices. So in the absence of disorder, the system is a Mott insulator. There is only on-site interaction. So they prepare Coulomb interaction. They prepare this 2D system. And what they can do is, at time equals 0, they can remove 1/2 of the atomic population, let's say from the right side. And then they can measure the imbalance in the densities or in the atomic population between left and right sides as a function of time. And in the experiment, they can also tune the disorder. So basically, here is the result for this imbalance. The green data points are for 0 disorder. We can see that the imbalance goes to 0 very rapidly, so the distribution of atoms becomes uniform very quickly. But as you keep increasing the disorder, you see that for high enough disorder, this imbalance persists at long times. And this was taken as evidence for many-body localization. Now, so again, the key requirement is for the system to be well isolated from the environment, which these systems can do, but it's an experimental system, so there is always some residual, coupling.
Why many-body and not simply Anderson organization?
Have interactions, many, yeah.
But could they prove that interactions are really doing something?
Probably, but I'm not. I think both are important, but I'm not, sufficiently familiar with those theoretical.
I think they can control that.
Yeah, they can. Yeah, they can control both. Yeah, but not in this experiment. So, and this was the on-site interaction. Yeah. So, yeah, maybe not necessarily in this experiment. So anyway, if you wait, so this imbalance persists, but if you wait long enough, because there is always some residual coupling of the system to the rest of the world, this many-body localization will be destroyed. And indeed, they actually, so this disappears after a while, and later they studied this systematically by increasing this coupling to the bath on purpose. And they found that when the coupling to the environment is larger, the thermalization it occurs faster, which is what you would expect. So even here, they're not, in these experiments, they're not truly in the MBL phase, but they're close enough to the MBL phase so that on short enough time scales, they can observe this, the persistence of imbalance or lack of relaxation. So there was also some theoretical work that I have a reference later, I think, in addition to this, where they show that this sensitivity to the coupling to a thermal bath is strongest near or at the phase transition, basically between MBL phase and the thermalizing phase. So again, the key difference from glassy systems is that MBL is strongly sensitive to coupling to a thermal bath, and it was proposed that this can be used as a key experimental signature as a way to distinguish these different, one of the ways at least, or the way, to distinguish these different types of dynamics. Okay, so I already mentioned that this is one limitation, but this is true for all experimental systems. I think here the maybe time scale, typical time scale as far as I know is of the order of a millisecond. After that, thermalization takes place. The other limitation is that these systems are relatively small. I think the largest ones have 10,000 atoms, but typically they're smaller. So the interpretation of some experiments and most numerical simulations, which are even smaller, has been a challenge. So it is really desirable to try to study these problems, this type of dynamics in systems that are larger, that are closer to the thermodynamic limit. So this is where, you know, solid state materials come in. We have many more electrons there. We are much closer to our thermodynamic limit. And the experimentally relevant power law interactions, their effects have been studied theoretically in great detail, in particular exploring the role of the range of the interaction and the dimensionality. This case, for example, has been under debate theoretically. And again, as I said, every experiment has some finite coupling to a bath. The challenge for electronic systems is that electrons are typically strongly coupled to phonons. So it's very difficult to isolate them from the environment. So we need a system where this coupling is sufficiently weak so that on short enough time scales we can observe MBL. And because of this coupling, any experiment really can be done, strictly speaking, in this pre-thermal regime. So I will show you that this 2D electron system, which is formed in silicon metal oxide semiconductor field effect transistors, is really an excellent system for studying these types of dynamics. Well, one advantage is that this is an old system. The system in which 2D behavior of electrons was first discovered almost 60 years ago. It forms the basis of, you know, modern electronics, which means that technological aspects, material aspects are well understood. So this is an advantage. And this is a gated device, so we can change the total electron density in a 2D layer by changing the voltage on the gate. So this change can takes place relatively quickly. In silicon MOSFETs, it's of the order of 50 picoseconds. In our case, because we are interested in the low density regime where system resistance is large, this time is typically at most 5 nanoseconds, which is much smaller than our experimental resolution of about 1 or 2 seconds. So in other words, within our experimental resolution, we can perform an instantaneous change of the total electron density. In other words, this allows us to perform a quantum quench experiment. So we can that way prepare the sample, the system, to be far out of equilibrium, and we can perform studies of the dynamics for different densities, starting from the high density metallic regime to the low density insulating regime as we go through the metal insulator transition. And let me just emphasize that unlike the talks we've heard earlier today and maybe yesterday, we are not talking about finite temperature phase transition. This is a zero temperature quantum metal insulator transition. So we can perform this quantum quench, but for MBL, what is important is to be able to isolate the system from the environment. And here is where silicon comes in, because it has been known for a very, very long time that in silicon at sufficiently low temperatures, the electron-phonon coupling is weak, so it's basically negligible. The heat transfer occurs is dominated by electron diffusion through these contacts labeled source and drain up the measurement leads that go to the top of the cryostat. And if we put the system in vacuum, as I think all low temperature experimentalists know, the system is even more isolated from the environment. So this is what our setup is going to be, unless I tell you otherwise. So we are able to, at low enough temperatures, to reach, and these temperatures are really not that low for low temperature measurements. Okay, so the other thing is that, in this system, the disorder is due to the positively charged sodium ions that are randomly distributed throughout silicon dioxide that are frozen below about 200 Kelvin. And so they're spatially separated from the 2D electron system, and they form this smooth random potential that 2D electrons feel. And in addition to that, we have a Coulomb interaction, which is a 3D Coulomb interaction, 1/r. Now, we have to recall also that because we have the gate, strictly speaking, due to the screening of the gate, this Coulomb interaction is modified because each charge has an image charge. So in addition to 1/r, we have this term that describes the interaction of an electron in a 2D layer with the image charge of another electron. And if at large distances, this is reduced to a dipolar interaction. So in other words, if our metallic gate, the screening gate, is far enough from the 2D layer such that that distance is much larger than the mean carrier separation, the Coulomb interaction is 1/r. On the other hand, if the gate is very close, such that the distance to the gate is smaller than the mean carrier separation, then this interaction assumes a dipolar form. And this condition can be reached, obviously, more easily or at lower carrier densities. So this is what we have used to investigate, actually, the effect of the Coulomb interaction on the dynamics of this system. So we had two sets of silicon MOSFETs. They both have a strong disorder, as you can see by this very, very low mobility. So the difference is in the thickness of the oxide. In the so-called thick oxides samples, we have the Coulomb interaction is 1/r. And in the case of thin oxide samples at low enough densities, it assumes a dipolar form. Now, importantly, these two sets of devices were fabricated simultaneously. There are more than 100 steps in this fabrication process. They were all identical. The only difference is in the thickness of the oxide. So if there is any difference in the behavior of these two systems, it must be due to the difference in the range of the Coulomb interaction. Okay, so before I discuss the dynamics, I have to say a few words about equilibrium transport. So this is something we studied in these two sets of devices many years ago, as you can see. Here, these plots show the conductivity as a function of temperature for different carrier densities, as shown here, going from high carrier densities to low densities. At high densities, the temperature dependence is very weak, and this has been known for decades in these strongly disordered silicon MOSFETs. As we reduce the carrier density, the temperature dependence becomes stronger. You can see that at the lowest densities, it's exponential in both cases, and both systems undergo metal to insulator transition at critical densities that are comparable. So I don't have time to show you in detail how we determined the critical densities, but I will just summarize what we have done. Basically, we have looked at the temperature dependence in detail, and this sketch here is a summary of our conclusions. So at the lowest densities, we find exponential temperature dependence of the conductivity, which means that in the zero temperature limit, conductivity is 0. And at densities, higher densities, there is this intermediate regime where we find this behavior. Phenomenologically, we determine that it's proportional to a temperature to power of 3/2. Now, this temperature dependence extrapolates to finite value at 0 temperature, which means that this is a metal, strictly speaking. So again, we are talking about zero temperature phase transition. The only difference between these ground states is that at zero temperature, in the insulating state, conductivity is zero. On the metallic side, conductivity is not zero. So, and by tracking how this zero temperature conductivity changes with density, we are able to, again, obtain see that this goes to zero at exactly the same value of the critical density. So we get agreement from both sides of this density consistent with, which strongly suggests that this is a metal to insulator transition, and we are able to do scaling and so on. Now, importantly, all this takes place in the regime where KFL is less than 1, where the mean free path is smaller than the wavelength. Yeah. Excuse me? Yeah, it's like, yes. Yeah, interactions, yes. Yes, I mean, they're always there. So, yeah, I mean, we could not have a metal in 2D without interactions in the first place, or a metal insulate transition. Okay, so, I mean, okay, all right, let me, so many of the, we have done much more work than this, and many of the results that we have found are consistent with a theory by Vlad Dobrosavljevic, who describes this 2D metal insulator transition as a Mott transition in the presence of disorder. So, yeah. Yes, yeah. Yes. Okay, so yes, so this KFL is less than 1. So everything that I will be discussing takes place in this regime where disorder plays an important role. So the conductivity, yes, this is a metal, but the conductivity is really very low. So, this is usually called a bad metal. Okay, so now I think I want to discuss the dynamics. And so I will focus in this talk on only one protocol. And we perform the same protocol in both sets of devices. So I want to compare that. So the protocol is very simple. Maybe it's better not to read this. So the protocol is shown here, and these are the data. So what we do is start from high temperature, high density, where nothing interesting happens. We cool the system down to the measurement temperature. And then after some time, it doesn't matter how long we wait, we reduce the carrier density by a large amount. So we are taking the system very far from equilibrium. So this is time equals 0, and then we follow the evolution of conductivity with time. So at time equals 0, because we are reducing the carrier density due to the field effect, the conductivity drops immediately, but it does not stop at this red dashed line. Instead, it overshoots it, in this case by more than order of magnitude, and then it starts slowly approaching this line here. And note the time scales of the order of 10 to 4 seconds, 10,000 seconds and more. So it's these are long, time-consuming experiments. And then when we see that this almost has saturated, we warm the system up to high temperature, cool it back down again at that same density to just verify that we waited long enough. So this seems to be the equilibrium value for this average conductivity. So that's what I will call it. So this is one experiment for one density, one temperature. Now for the same density, you can repeat these measurements at different temperatures. You get a set of curves, and you put them all in one figure. And note, so each curve corresponds to different temperature. What we are plotting here is the conductivity for a given temperature normalized by the equilibrium value at that temperature. So that on this logarithmic scale, this 0 here corresponds to the equilibrium conductivity for each of these curves. So you can see as we reduce initially, as I said, the system goes away from this equilibrium value. Then at some later time, it approaches the equilibrium. As you reduce the temperature, this minimum shifts to longer and longer times until it falls out of our experimental time window. So now if we focus on what happens at these intermediate times before the minimum, we can see that even from, well, not from here, that this is not an exponential relaxation. And in fact, we are able to collapse all of these curves onto the same curve and show that they can be described by this function, which is a product of a power law and a stretched exponential. And in the zero temperature limit, this is reduced to pure power law. So it seems, based on this, that at zero temperature, strictly speaking, we have a glass transition. And it's interesting that exactly the same time of dynamical scaling was obtained in conventional spin glasses. What? I just started. Oh, no, I have so much, yeah. Okay, yeah, all right, in the, above, the glass transition temperature. I need to get to the most important things. Okay, so if you look at the approach to equilibrium, this is a simple exponential process. You can extract the characteristic thermalization time, like everybody has been doing, and you already saw that it depends very strongly on temperature. In fact, it diverges in the zero temperature limit, which again tells us that there is a glass transition at zero temperature. So we have studied this glassiness using also other protocols similar to what people do in other types of glasses, like spin glasses. And again, this is a sketch of our conclusions. So there is a well-defined density, glass transition density, below which there is a zero temperature glass transition for each of these densities. So this insulating phase is glassy, and this intermediate phase is also glassy, but they're not the same kind of glass. And at low enough temperatures, we see this on short enough time scales, we see glassy behavior. And again, at temperature about 1 Kelvin, the thermalization time is actually orders of magnitude longer than the age of the universe. So it doesn't really matter that we are not truly in the glassy regime, which occurs at zero temperature, but on experimental time scales, the system is glassy. So let's do the same, perform the same protocol in the system with the screen-cooling interaction. So here we see this, do the same thing. We reduce the carrier density instantaneously, conductivity drops. Eventually, similarly long time scales that approaches this equilibrium value. So again, we perform measurements for different densities, temperatures, and so on. And let me now compare these two, the behavior of these two systems. So in the case of a long-range interaction, I already explained that we have these non-exponential relaxations. This is just an example of the behavior at a different density. Now, in the case of a short-range interaction, for essentially the same density, this is what we get. So the curves, you can see, they look qualitatively different. So if you focus on intermediate times, you don't see these non-exponential relaxations. In fact, the relaxation is negligible, which is what you would expect in the case of MBL. So we do not see any evidence of glassiness here. But what is most striking is really the behavior at long times, because at long times, we no longer have this temperature-dependent thermalization time, but instead all of these curves seem to reach equilibrium at basically the same time. And in this case, this process is also simple exponential. So we can extract the thermalization time for different temperatures, densities, devices, and so on. And this is what we get, no systematic dependence on anything. The thermalization time is of the order of 10,000 seconds. So the question is, again, is this consistent with MBL? So here we recall that MBL should be extremely sensitive to a coupling to the external bath. So just like the other people, we cannot reduce this coupling further, but we can make it stronger. And we can do that, for example, by repeating some of the experiments in helium vapor, which is what we did. And when we did this, we saw that these 10,000 second thermalization times were reduced by an order of magnitude, which is again consistent with the expectations for MBL. So these experiments, these measurements were done at below 2 Kelvin, where electron phonocoupling is very weak. You can go to higher temperatures where coupling by phonons, cooling by phonons, or thermalization by phonons dominates. And we found that the thermalization time dropped by at least another order of magnitude. So we have a very strong, maybe even exponential dependence on the coupling to a bath, in contrast to what we found in the case of glassy dynamics, where even at higher temperatures, we do not see any change in the glassy dynamics. So what we found is that, yes?
How do you achieve short range
Interaction?
streaming?
Yeah, the thin oxide, the gate is much closer to the...
But then you have basically a coupling to a dissipation path, which is a gate, isn't it?
but how is it coupled? Okay. Well, that's obviously not sufficiently strong to make a difference. Or, yeah. So maybe this is, maybe that contributes to thermalization at longer times, but obviously. So this does not change. I mean, when this remains fixed, right? I mean, if it's there is some coupling to a bath, this way or that way, but it's sufficiently small that we can see MBL on these long time scales. And in these measurements, we do not change the distance to the gate. So we just, yeah.
So you cannot be
Yeah. Okay, yeah, the last second, so, okay. Yeah, I mean, right. So the conclusions are here. So there is a, obviously strong effect of the change interaction range. So in the long range, the dynamics is thermal, but although glassy. And in the case of a dipolar interaction, it's consistent with MBL. And this is actually this situation that was under debate theoretically. So the result seems to support those arguments, those who argue that true MBL cannot exist in this regime. Now, again, we do have some finite coupling to a bath, which is, and dependence is very strong. So if we could make it go to zero, we could speculate that maybe we would be in a true MBL phase, but I think we'll never know. So anyway, the conclusion is that when KFL is less than 1, when the disorder becomes important in these 2D, strongly disordered 2D systems, you see slow dynamics. Glassiness is observed when Coulomb interaction is 1/r. And importantly, glassiness does not survive when the interaction is screened. And this was actually our original motivating question for these studies. But instead, we see in sufficiently isolated systems, MBL. So what is important is that we establish a new solid-state platform for studies of MBL in large systems, and now we can address other questions that are of great interest right now. In particular, what people are interested are additional differences between the glassy and MBL regime. So here are some studies that we can do. Actually, we are doing some of them already, and of course, it would be nice if there could be some other solid-state platforms, but remember, we don't want phonons or, strong coupling to the bath. So thank you very much.